Welcome to Paper Trail, where we make academic research accessible and engaging. Let's see what the evidence says. A landmark study has just revealed that nearly half of social science findings fail to replicate when tested by independent researchers. And even when they do, the actual impact of those findings often shrinks dramatically, sometimes by over 80%.
That's right. It's a sobering assessment, but also one of the most rigorous and comprehensive audits of scientific credibility ever undertaken. It forces a reconsideration of how research is interpreted and applied, shaping everything from public policy to daily headlines.
So, if findings are essentially a coin flip, and their true impact might be a fraction of what was originally claimed, how much of what is commonly understood is built on sand?
That is precisely the question this project, known as SCORE, set out to answer. It's an unprecedented stress test of the social and behavioral sciences.
The scale and ambition of this project are difficult to overstate. 865 researchers globally mobilized to essentially check the homework of their peers. What was the driving force behind such an enormous undertaking?
The initiative, the Systematizing Confidence in Open Research and Evidence Project, or SCORE, was spearheaded by the Center for Open Science, but it received significant funding from DARPA, the U.S. Defense Advanced Research Projects Agency. And that might seem counterintuitive at first glance. Why would the military be so invested in the reproducibility of social science?
It does seem like an unusual pairing. One might expect DARPA to be focused on AI or advanced weaponry, not the nuances of psychology papers.
Exactly. But the Department of Defense, like any major policymaking body, relies heavily on insights from fields like behavioral economics, psychology, sociology, and political science. This research informs everything from training protocols and intelligence analysis to psychological operations and geopolitical forecasting. If the foundational research underpinning these decisions is flawed, the resulting policies and strategies are built on very shaky ground. DARPA's ultimate goal was highly ambitious: to develop tools that could assign confidence scores to different social and behavioral science research results.
So it wasn't just about identifying problems, but about finding a way to proactively assess the reliability of studies before they're used to make critical decisions.
Precisely. They extracted nearly 4,000 claims from papers published between 2009 and 2018, spanning 62 journals across 11 diverse disciplines. This wasn't some niche corner of academia. It was a broad cross-section of the literature. The sheer administrative and scientific willpower required for this kind of retrospective audit is remarkable. Science is typically geared toward discovering the next new thing, not meticulously re-examining the old.
It really underscores the idea of science as a self-correcting process, even if that correction is a massive multi-year undertaking involving hundreds of institutions. Before delving into the specific findings, it's important to clarify some key terms, because the SCORE project makes very precise distinctions that are critical to understanding its results. What's the difference between reproducibility and replicability?
That distinction is absolutely fundamental. In metascience, precision is everything, and these terms often get conflated in public discourse, but they measure entirely different aspects of scientific validity.
To begin with reproducibility, what does that mean in the context of this study?
Reproducibility means running the exact same analysis on the original data. Think of it like auditing an accountant's spreadsheet. You have the exact same receipts, that's the data, and the exact same ledger, which is the code and analytical steps the accountant used. The question is, if you punch the numbers into a calculator using the same method, do you arrive at the same profit margin the accountant reported? Reproducibility tests the transparency and accuracy of the math.
So it's about whether you can get the same answer if you follow the same steps with the same inputs. What about replicability then?
Replicability is a much more demanding test. This requires gathering brand new data to test the same underlying research question. The analogy here is like opening a second franchise location of a successful business. You're using the same business model, the methodology, but you're testing it in a new town with new customers. You're collecting new data, in other words, to see if the phenomenon actually holds up in the real world, outside of the specific context of the original study. Does the business concept work in a new environment?
That distinction is crucial. One is about verifying the calculation, the other is about verifying the phenomenon itself. Before they could even get to the replicability test, the SCORE team ran into a significant hurdle, didn't they? The transparency roadblock.
They did, and it highlights a systemic issue. The report revealed that data was available for only 24% of a sample of 600 assessed papers. For 3/4 of published social science, the original authors had not shared the raw data required to even verify their findings. This lack of transparency makes independent assessment, even just reproducibility, functionally impossible in many cases.
That's a staggering figure. It means you can't even check the math for most published studies.
It's a massive barrier to scientific progress. However, when the SCORE reviewers could get their hands on the data, the results were highly illuminating. For the 143 papers where they attempted a reproduction, only 54% could be precisely reproduced. Another 74% could be approximately reproduced, meaning the result was within a close margin of the original.
But there was a transparency dividend, as the report calls it, when authors did share their data.
Absolutely. When the original authors had proactively shared their data and analytical code openly, exact reproducibility skyrocketed to 77%, and approximate reproducibility jumped to 91%. This is a highly actionable takeaway for listeners. The data proves that methodological sloppiness, or bad math, isn't an unchangeable law of nature. It is a direct consequence of closed systems.
So if journals just demand transparency, the rigor improves dramatically.
It's an infrastructure win. The SCORE project found that political science and economics, for example, dramatically outperformed other fields in reproducibility. This wasn't because economists are inherently better at math, but because their leading journals instituted strict data and code sharing mandates years ago. When transparency is required, the quality of the science instantly improves.
That's a powerful argument for open science practices. But the real headline grabber, the stress test that everyone is talking about, is the replicability phase. What did they find when they went out and collected new data?
This is where we hit the coin flip survival rate. In the replication phase, independent researchers gathered fresh data to empirically test 164 previously published papers, which encompassed 274 specific claims. The most striking finding was that only 49.3% of those 164 papers successfully replicated. If you look at individual claims, it was 55.1%.
So roughly half of what was published didn't hold up when someone else tried to find the same phenomenon with new data.
That's the reality. And successful replication here meant the new study achieved statistical significance with the same pattern and direction as the original study. To break it down further, only about a third of the new analyses yielded results that were very close to the original study's numbers. In about a quarter of the cases, no clear effects were found at all. The phenomenon completely vanished. And in around 2% of cases, the results actually pointed in the exact opposite direction of the original claim.
That has profound implications for policymakers, journalists, and frankly, anyone who makes decisions based on social science research.
It absolutely does. Imagine a mayor deciding to fund a new multi-million-dollar anti-poverty intervention based on a single study published in a prestigious sociology journal. The SCORE data suggests there's roughly a 50% chance the intervention's foundational premise will not hold up when applied to a new population or in a slightly different context. Every day, science journalists write definitive headlines like, "Study proves X causes Y," and policymakers draft legislation based on single, newly published papers. This data suggests that half the time, that foundation is incredibly fragile.
It's important to clarify here that a failure to replicate doesn't necessarily mean the original researchers were fraudulent or intentionally sloppy.
That's a critical point to emphasize. A failure to replicate does not automatically imply fraud. Human behavior is incredibly complex and context-dependent. A psychological intervention that worked on a cohort of university undergraduates in 2011 might genuinely not work on a diverse sample of adults in 2026. Context changes, populations change, and small differences in methodology can have large effects. But the 50% failure rate highlights a systemic issue. The scientific literature is filled with findings that are treated as universal truths when, in reality, they are often fragile, context-dependent observations.
And even when studies did replicate, the SCORE project uncovered another unsettling truth. The magnitude of the effects often shrank dramatically.
This finding is perhaps the most subtle but devastating for the practical utility of social science. Even when a study successfully replicated, meaning the new data confirmed the phenomenon actually exists, the SCORE project revealed a median reduction of more than 50% in the estimated effect size. And crucially, the explained variance dropped by over 80%.
To break those terms down, because effect size and explained variance might not be immediately clear to everyone, what does a 50% reduction in effect size actually mean?
Effect size measures how much of a difference an intervention makes. So, if an original study claimed a new teaching method raised test scores by 20 points, a 50% drop in effect size means the replication found it only raised scores by 10 points. The effect is still there, but it is vastly less impressive and less practically significant. It means the intervention is half as powerful as initially thought.
And the explained variance dropping by over 80%? That sounds catastrophic.
It is. Explained variance, often denoted as R squared in statistics, measures how much of the variation in an outcome, as opposed to random noise or other factors. So if an original paper claimed their intervention explained 15% of the variance in employee productivity, the replication found it actually explained less than 3%. The original signal was nearly drowned out by the noise in the replication. This makes the finding far less useful for prediction or policy intervention.
Why does this happen? Why do effect sizes shrink so dramatically in replications?
A primary driver is what's known as publication bias and the winner's curse. Academic journals are highly competitive and heavily favor publishing novel, statistically significant, and large effects. Imagine 10 different research teams testing a subtle psychological phenomenon. 8 might find nothing, 1 might find a tiny effect, and 1, purely by statistical chance, might find a massive effect. That team with the massive effect gets published in a top-tier journal. The other 9 often end up in a desk drawer.
So the initial published finding often represents a kind of best-case statistical scenario.
Exactly. The original researchers might have, even subconsciously, engaged in p-hacking or exploited researcher degrees of freedom, tweaking their analytical models or data exclusions until they achieved the largest possible effect size to secure publication. When an independent, dispassionate team runs the exact same experiment without that incentive to find a massive result, the true, much smaller effect size often reveals itself. This fundamentally changes how new studies should be viewed. The initial finding should be seen not as the definitive measurement of a phenomenon, but as its maximum possible upper bound. The reality is almost always smaller, messier, and less impactful.
That's a profound shift in perspective for how to consume scientific news. Moving to the cutting edge of this project, SCORE also tried to answer a crucial question. Can we predict which papers will fail to replicate before we spend all that time and money testing them? They set up a forecasting tournament, pitting humans against machines.
This was one of the most innovative elements of the project. Because empirical replication is incredibly slow and expensive, DARPA wanted to know if they could develop tools to predict credibility. So they set up a massive tournament, comparing human expert judgment against artificial intelligence and machine learning algorithms.
And what did they find? Which came out on top?
The humans performed remarkably well. Independent teams of human forecasters, like those from Replicats and Replication Markets, evaluated the papers. They looked at sample sizes, the plausibility of the claims, methodological rigor, and statistical reporting. The report shows that human forecasters achieved up to a 78% success rate in predicting replicability using the best performing metric.
78% is quite high for predicting something so complex. What does that tell us about human expertise?
It suggests that experienced researchers possess a finely tuned BS detector. They understand the nuances of experimental design, they know which subfields are prone to exaggeration, and they can spot when a claim is too neat, too perfect, or too large to be true. It's a testament to the value of deep, contextual knowledge and critical thinking.
So human skepticism triumphed. What about the algorithms? How did the AI fare in predicting bad science?
In stark contrast, the initial machine learning and algorithmic methods developed by teams at various universities and tech companies largely failed to effectively predict replicability.
That's surprising in an era of such rapid AI advancement, where algorithms are pitched as solutions to everything from content moderation to fact-checking. Why did AI struggle here?
Machine learning excels at finding patterns in data, but assessing scientific credibility requires deep contextual reasoning. An algorithm can easily check if a p-value is below 0.05 or scan the text for certain keywords. But evaluating whether an experimental design actually isolates the variable it claims to be testing, or whether the theoretical framework makes logical sense, requires a level of semantic and scientific comprehension that current AI models simply lack. As one of the project leaders, Brian Nosek, noted, a lot more evidence is needed before we would be confident in a valid, scalable solution regarding automated credibility scoring.
So for all the hype, when it comes to the complex, high-stakes world of scientific validity, algorithmic fact-checking isn't ready to replace human scientific skepticism or deep human peer review.
Not yet. The project demonstrates that human critical thinking remains irreplaceable for now.
This SCORE project provides much to consider. What are the key takeaways for listeners and for society in general on how to approach scientific findings moving forward?
There are three critical insights. First, the distinction between reproducibility and replicability is not academic pedantry. It's vital. One tests the transparency of the math, while the other tests the underlying truth of the phenomenon. It cannot be assumed that a finding is true just because the math is correct.
And second?
Expectations of scientific breakthroughs must be recalibrated. The massive 50% drop in effect sizes and 80% drop in explained variance when independent researchers repeat the work proves that early science is almost always louder than reality. An initial finding is often a maximum, not a definitive measurement.
And finally, a path forward, perhaps?
The third takeaway is that transparency is a powerful cure. The replication crisis can seem overwhelming, but the SCORE project offers a clear, actionable fix. Exact reproducibility skyrocketed from 54% to 77%, simply when original authors shared their data in code. Open science mandates. If funders and journals require researchers to show their work, the structural integrity of the entire scientific enterprise improves instantly.
That makes a lot of sense. But if open data works so well, why is the data sharing rate still so low, around 24%? How do we change the academic tenure and grant funding systems to reward rigorous, transparent, incremental science rather than just flashy, single-study breakthroughs?
That's a fundamental challenge to the incentive structures within academia. It's not just about what is scientifically sound, but what advances careers.
And what about the future of AI in this space? While human forecasters dominated the machines in this project, AI is advancing rapidly. Will we eventually reach a point where an AI can ingest a PDF of a study and instantly flag methodological flaws that humans might miss? And if so, how will that change the peer review process?
The potential is there, but the SCORE project serves as a crucial reminder that true understanding often requires more than pattern recognition. It requires interpretation and judgment.
The SCORE project does not indicate that science is broken. It suggests that science is working exactly as it should, by finally turning its exacting, skeptical lens upon itself. That wraps up this episode of Paper Trail. Join us next time as we dig into more research worth talking about. If you liked what you heard, share it with a friend.
Keep reading the fine print.